video, let's get into how to do regression in Excel. Now, if you watched the earlier videos, you would have already seen how to get to correlation using a formula. And regression does build off of some of the same math behind how we got to a correlation. And so we're going to use the same example of working with the variables around age and distance from home. I want to show it to you next to where we did correlation, so I'm going to go ahead and put it on our current sheet. And once you press OK, wherever you had selected the output to go, you are now going to get regression summary output. Now, what this output is giving us here is it is giving us some different statistics, and I'll sort of walk you through what some of these might mean. It's giving you what they call a multiple R. Now, this does just use R, which is, if you're only using two variables, is the same thing as the correlation that we did in our earlier example. So that is often called a Pearson R. And if using only two variables, it will be the same number. So you'll see here that when we did Corel, it ended up as a negative 0.001686. And here we have a 0.001686. Same value in terms of number, but a different direction. So when we did the correlation the first time, it came out negative, meaning that as one variable was increasing, the other was decreasing. What regression does is it doesn't put the direction here, because there can be future versions of this, which I will show you, where you can put multiple variables in, and then this number will change quite a bit. So this similarity only exists when you're working with just two variables. But it does still give you that sense of how much correlation is there between the variables that you're looking at here. It will also give you the R squared. Now, the R squared is literally the square of the R. So if we were to take this number up here, and if we were to use a formula to say, take this number that we already got and multiply it by itself, we will get a number that looks just like the one that we have from the table. So it is just squaring this multiple R number. And the reason that we do that is we can use this R squared number as a measure of strength. Typically, the way that we talk about an R square is to use it as a way to discuss the amount of variance in our dependent variable that we can explain by our independent variable or variables. So in this case, it's a really small number, so not a lot is explained. Whenever you see this E minus and then some numbers after it, that's actually telling you that there's a ton of zeros in front of this. So this is telling you that this is not 2.8. This is a scientific notation for what is basically putting 6 zeros before where the decimal place currently is. So you'd have to go 1, 2, 3, 4, 5, and a 2 for 6, because that's how many times we had to move the decimal place over. And so that notation means a 0.00000, I don't know how many zeros I said, 5 zeros, and then a 2 and an 8 is our R squared. So this is really low. There's almost no variance explained in terms of somebody's distance from home being explained by their age. Again, kind of expected that because our correlation was practically nothing. But this is how we would think about it. Now, you will also get something called an adjusted R square. This is the math being used to account for additional variability and error that might be in your statistics. This is really important if you start to add more variables. So if we had more than just age predicting it, then you really want to pay attention to this adjusted R square. It's basically taking this number up here and then factoring in some other things around the number of variables and different pieces of error that might be coming in, and it's using the standard error, as well as your what we'd call sample size. How many observations or pieces of data are we working off of? So that is kind of one of the first pieces around regression that we look at. We typically want to look at an R-square or an adjusted R-square to say how much variance in the thing that we want to predict or know about can be explained by the thing that we're using to predict it. In this case, it's super low. The other thing that we want to typically look at is this ANOVA results. And specifically, we want to look at this piece called the significance F. Now, this is what we look at, and it's also called the p-value. And it is looking at whether or not there is a statistically significant interaction and outcome with the variables that we used on this particular regression model. Now, ANOVA is a whole nother analysis and needs a whole nother video, so I won't really go into the details of what all of these pieces mean, but usually we do like to look at this significant F here, and we're hoping that it is a very small number if we want to be able to say that this is a statistically significant model. Typically, you want a number less than a 0.1 or a 0.05 or even less than a 0.001. So a really, really tiny number, as close to zero as you can get. In this case, this is a horribly big number. This is not a significant model. Again, no surprise here. We knew there wasn't a correlation when we started. And then your final piece, and this is a really helpful last part of the table, is your coefficients table. Now, what this does is it gives you some coefficients. The first is called an intercept. The idea of the intercept is that simple linear regression is based on a line, hence linear. So when it's predicting something, it's saying as age increases, then distance from home, decreases or increases. And this intercept tells you how to draw that line if you were going to put it on a chart. So it basically says the point at which the line is going to hit 0 on the y-axis. So, if you're going to make yourself a little chart, you'd start the line here. So in this case, that's just where it would start from 0. And then for the variables that are given coefficients, that's telling you how you'd actually draw the line. If you know the definition of a line, sometimes you'll see it as y equals mx plus b. But you could then plug these variables into that line, and you would use it to be able to talk about the relationship between the variables. So for example, in this case, we would say that because this coefficient is a negative number, that means that as age becomes larger, meaning a larger number, then distance from home would go down. And that's the idea of a negative correlation. As one variable goes up, the other one goes down. If you see a negative coefficient here, that means a negative relationship, meaning one goes up, the other goes down. If it was positive, that would mean as one goes up, the other one goes up. So we use the line to say that for each additional year in age, and I only say year because that's how our data was set up, it was in years. For each additional year, we would expect distance from home to decrease by 0.00149 miles. And again, that's just because this particular data was set up with that as its measure. Now, that's a really small amount, so we'd say that there's really not that much difference at all. And then we're going to have quite a few other variables. They are all really important, but for the sake of keeping this video short, I'm going to skip a couple important ones. Error is very important, so is the t-statistic. But let's just go to the p-value. So this is similar to what I was describing with the significance F being a p-value. And we are looking to see if this variable, age, statistically significantly predicts distance from home. And we would get that sense if these numbers were very, very, very small. A joke I like to make is think about P, like P-E-E. If you had to have some pee get on you, how much would you want? Yeah, you'd probably want as little as possible, preferably as close to 0 p on you. That's usually what you're looking for when you're looking at statistical outcomes. You want a very, very small p-value. That is a sign that it's statistically significant. In this case, the intercept is very, very small, but because we have e to the negative 25, so that means move the decimal point to the left 25 spots, but age is not. This is actually the same value we saw in the significant F outcome. And that will be true anytime you're only working with two variables, one y and one x. If you start to do multiple linear regression, where maybe you have more variables, then you will see that this F value is going to indicate all of the variables together, and then it won't necessarily be the same as down here. But for right now, they're the same. And then what Excel does is it actually gives you some confidence limits. By default, it fills in the 95% confidence limits. For the sake of this video, we're gonna skip that, though again, that is also fairly important. So once you've done this regression, you would look at this and say, there is not a relationship between age and the distance that someone lives from their home to their work. And we can see this because the correlation is so close to 0. Very little of the relationship or the variance in distance from home is explained by age, and it's not a significant value when using it to predict distance from home. So if you ran this, you would say, nope, there is not a relationship. Now, one thing to keep in mind when doing things like this is no finding is often a finding. So this would be useful because someone that you work with might have the assumption that distance from home is related to age. Maybe they do think there's certain patterns. And you can say, well, actually, with our employee data, there's not really evidence that our current employees fit that hypothesis. We don't think that age and how close someone lives to work have anything to do with each other. And that could help with your decision making around plans with, say, commute resources and other types of outreach efforts. So hopefully this helped you see how to run regression in Excel. There'll be one more video showing you how to do it with multiple variables, and we can talk a little bit more of that one.